Good morning, delegates. I'm pleased to present the keynote address for this session, which is a review of membrane technology as a process tool. So first I'll go through a short introduction, a bit on membrane applicability, some contemporary membrane use, recent applications and pending applications, I guess, recent at Paladin, pending at Shawinigan. Some conclusions, a bit of outlook from my perspective, and then we'll close. I might add that I wouldn't claim to be the most knowledgeable expert on membranes, and that my knowledge is more applied rather than theoretical. But I do have recent direct experience in design, implementation and operational levels of a couple of NF installations that Paladin undertook. In fact, I'll be presenting a paper on those later today. So we look at membranes generally. Prior to the 70s, membranes weren't even generally more broadly used, industrial, with one realistic exemption. And membranes have been used commercially since the 50s, industrial, and that really is focused around the chlor-alkali application, and that's a well-established technology now, has been for a long time. In mining, the use has been limited really to water treatment for quality or environmental purposes, and in the early 80s, RO was introduced as an ability to convert brackish or salt water to drinking quality water, and soon became technology of choice for that use in mining. And there are some environmental applications. And most of the applications are RO or RO based. But there are many membrane classes with the potential applicability to hydromet. So microfiltration or ultrafiltration, nano, reverse osmosis, and then electrolysis, dialysis, electrodialysis, and a few more. Membranes are now used almost ubiquitously in the likes of food processing. So the concentrated fruit juice, the separation of enzymes, making non-alcoholic beer, if that were indeed your desired intention, and purification of vegetable oils, indeed the separation of separate fatty acids in vegetable oils, all done with membranes. And biotech applications too, the antibiotic production and protein purification. I missed one. The one I missed on food, the most obvious one, I guess, is milk processing, where in the bigger milk processing units, almost everything goes through a membrane. But this paper looks at applications that have recently been applied or have near-term potential in the mining industry. So we look at just where membranes sit in relation to different areas. So RO sits, is going to separate at around the 10 angstrom level and below, 10 to 15. NF sitting at sort of 8 or 9 and up to maybe 100 angstrom, 110 angstroms. Then above that you've got UF, MF, and then conventional particle filtration. So sitting at the same level as MF, of course, would be things like clarification or sand filters. I beg your pardon. So in terms of contemporary membrane use, membranes really now, I think, is certainly the mining sector, a technology of choice for water treatment for quality. And by that I mean, if we want drinking water, or if we want so domestic water, or if we need high purity water for reagent makeup or somewhere in process, RO it really is the go-to. Some mines, and I guess a good example of this is the Ranger uranium mine. Some mines are using membranes now for environmental discharges, and Ranger's in a situation going into closure and long-term rehab. The water they're putting into the environment now is better than is higher quality than the water courses that it's entering. So they're putting much higher quality water back into the environment than the environment has itself. And then we look at recent applications, and in 2013, Paladin undertook an NF application at Kalakira in Malawi. Then in 14-15, it did a similar installation at Heinrich in Namibia, and Namaska has been constructing the Shawinigan electrochemical plant now for a few years, and is attempting to complete that. That's a electrodialysis, or as they would describe it, a membrane electrolysis unit. And then I understand there's also been some work done on an ISR in Kazakhstan, a paper for which is to be presented later today, is my, well, according to the program. So to look now at the Paladin experience, NF was applied on 2 sites to recycle reagent contained in conch eluate. Those 2 sites, one was an acid leach and therefore acid circuit, that's Kalakira, and the other was an alkali circuit. So as far apart on the chemical spectrum, the pH spectrum anyway, as one could reasonably be in uranium processing. And the applications at each are surprisingly similar. They're for different reasons, and I'll give more detail on that in a paper this afternoon. They were done really for quite different reasons, but the processes in concept are almost identical. These two installations were both brownfields. They were both very, very successful, especially in commercial terms. In the Langer operation, we were able to, it's public data, the total process operating cost fell by about 50%. That's in anyone's language, that's a big reduction. And especially when one considers that Langer was already considered a lower cost quartile producer. And at Kalakira, not quite as a dramatic effect in terms of operating costs, but a 15% reduction in total process operating costs. So it's probably reasonable to say now that with those successful applications, successful commercial applications, in both alkali and acid process chemistry, that NF has been established as a commercially proven process. And that's a big leap for any process. And a little bit more on the Langer experience in particular, in that Langer may change perceptions as to the preferred route for uranium extraction. And I say that because my understanding, and I think it's reasonable, is the general perception of uranium processing is that it's likely to be an acid circuit unless it can't be. Langer was a case of that, a case in point there, highly acid consuming ore. It had to go alkali. But generally speaking, I think most would say if you don't have to go alkali, go acid. What was achieved at Langer may change that view. The alkali route is not solely applicable to Langer style mineralisation. Kintyre, for example, was tested for both acid and alkali leach. They took both to full detailed feasibility level. So, and indeed, the alkali process technically looked, my understanding is, a little better. But Langer there on a low grade resource, less than 500 or around 500 ppm U3O8, was recognised as a lower cost quartile operation, and that's quite, I think that's quite a leap for the technology that was at play, and potentially quite a leap for the industry, because alkali really does offer some pretty significant advantages, most notably in terms of impurity control, but also in the potential rehabilitation of the site. We're dealing in an alkali environment, so most of the metals that are problematic in rehab just aren't mobilised in an alkali environment. It's why the alkali route offers the potential advantages it does in terms of impurity in final product. There's very few metals are soluble. There are some naturally, but very few metals are soluble on the alkali side. So then, and I should just, one point I failed to mention there, this NF separation. So with NF, we're separating on the basis of valence. So we can keep the monovalent ions going through to the permeate side of the membrane, and in the retentate, all the higher valence ionic species are retained. This is a mode of separation that we just, to my understanding, we really haven't had before as an industry. And then you move to Schwerningen, and Schwerningen is based around membrane electrolysis cells, or really dialysis cells. And here the membranes discriminate on the basis of ionic charge. So there's cationic membranes and anionic membranes. You know, the cationic membranes let cations go through to the cathode, anionic anions through to the anode. That concept per se is not new in that chlor-alkali operates in similar manner with membranes. But in the membrane electrolysis or dialysis cell, you're not really trying to recover what you move into the move to either side as a metal or as a gas in the case of chlor-alkali. You're really trying to move stuff across and keep it in solution and take it out as a clean solution. And Schwerningen report that their membrane system is very successful at doing that, and they're claiming very high purity lithium hydroxide as a consequence of the system they developed, which is patented. From the literature available, this slide's a bit busy, but they effectively go from a 2-compartment cell where they take lithium hydroxide out of a lithium sulfate feedstock and end up with a combined lithium sulfate, sulfuric acid stream. That stream then goes to a lithium sulfate crystallizer, and the weak acid generated goes off back to leach, in fact, and the lithium sulfate is resolubilized and goes into a 3-compartment cell or bank of cells, where the complete dissociation occurs, and we get lithium hydroxide being formed in the catholyte and sulfuric acid being formed in the analyte, and both being taken away as value product, or either in the case of acid as a recycle stream, the lithium hydroxide off to crystallization and onwards to battery chemicals, no doubt. This plant's not yet operational, although in fairness, or perhaps not fairness is the wrong word, but it's worth noting that Nemaska have undertaken some quite lengthy commercial piloting of this process and have now years of operating data. So at small scale, it's certainly established, and I think a lot of buyers will be on Schweiningen in terms of, obviously, it's an emerging lithium producer, but aside from that, just how well these membrane cells go. And of course, there's further application of membranes at both the Langer and the Carlacera site with Paladin feed prep, which is critical for NF. It's the potential Achilles heel of the process. Both installations for Paladin used UF ultrafiltration as a pre-treatment step. Was done in combination with clarification, and it's possible that we could replace the clarification part of that with microfiltration, so go effectively a full membrane deal. And the other side to that, I've got it here in feed preparation, it's consequential too, but once solution's low in TSS, further membrane steps become relatively lower cost. A large part of the capital and operating cost of a membrane circuit is in fact the feed preparation of an NF circuit, I should say, is in fact the feed preparation for the NF. Once you've got those clean solutions, further membrane work is lower cost, relatively lower cost. And a good example of that would be in taking the permeate, for instance, and upgrading the tenor of that solution, so that on the retentate side of an RO, we start keeping all. In this case, it was the eluate reagent, sulfuric at Carlacera and bicarbonate at Langer. So you can concentrate those streams and at the same time get a pure or very clean water stream for further use in the process. We didn't go this far, but certainly the potential to do so is readily there. So where do we get to in terms of conclusions? Firstly, the mechanism for NF allows us now to separate ionic species based on valence. That's, to my mind, that's a huge step. We just haven't been able to do that before. And when you put your mind to it, we can play with the valence of many metals and anionic species for that matter, and get them down into a monovalent state. Not all, but many. So we're able to move them in one direction relative to everything else, or a lot of the other species in solution. Higher valence is the monovalent stay with retentate, and the selectivity is very high. Uranium selectivity at both Langer and Carlacera was 99.7. The sulfate and carbonate selectivity, which was the other two higher valence species present, was also very high in the high 90s. So these membranes are very, very selective. Electrodialysis, on the other hand, gives us the chance to discriminate on the basis of ionic charge. And so we can turn a lithium sulfate that's not particularly useful in battery manufacture to a lithium hydroxide, which is exactly what's needed for battery manufacture. And we can do it at very high purity, which is also critically important. So we've got 2 new process discrimination tools or separation tools in hydrometallurgy. And with those tools, some has demonstrated at Langer and Kayelekera in particular, some significant operating cost benefits compared to prior contemporary design. And I'm sure other applications will be identified in the months and years to come. I think it's fair to say that NF has now been established as a commercially proven process. Langer and Kayelekera both operated for long enough and well enough, I think, to firmly establish that. They certainly operated long enough for us to establish, basic commercial data like membrane life and the like. And electrodialysis at Schweiningen may well soon be established as commercially proven also, given the pilot work that they did. One would assume that that's the outcome, but we shall see. So in terms of outlook, this is a keynote, so it's, I guess, got to be a little bit esoterical and certainly glass half full. The new tools, I think will change preconception regarding processing options. My predominance of my work is in the uranium space. Alkali processing is not what used to be the dark horse of the industry. I just don't believe it is anymore. I think that will change materially. I do believe that membranes are likely to be used at an increasing rate in hydrometallurgy. The level of success achieved at Langer, halving of process operating cost from what was already a low-cost operation, simply can't be ignored. I think the application spectrum, and I don't think this is rocket science at all, the application spectrum will broaden as new applications come on. The industry is tremendous at innovating. I think membrane pressures will further increase, improving efficiencies. I think membranes will be developed with hydrometallurgical applications in mind. You've got to remember that the membranes we've used today have been developed really for other purposes. And with the 2 Paladin applications in particular, and I suspect the Kazakhstani operation too, membranes were applied well outside manufacturing data or manufacturers' data for the product. So it's really pushing a product well beyond where we know it'll go, or we did know it'll go. And I think, and so once we have membranes developed for specific hydromet applications, we may well be in an entirely new paradigm. And in that, I'm certainly aware of some emerging materials, and particularly graphene, being looked at very seriously now for targeted membrane applications, and specifically in hydrometallurgy and other areas. And again, not really rocket science, but you've got to expect that efficiencies in terms of cost and metallurgical efficiency in metallurgy will also improve. It's just the way of things. So as new technologies come on, there is always material improvement in those areas. So I've got to say, in summary, I have a view that it's a pretty bright future for membranes. I think we will see them in areas that one wouldn't necessarily expect, and I believe that will happen with some rapidity, and with material, based on our experience, material commercial success. Okay, thank you very much.
Hello everyone, and thank you for joining us this morning for the session. We're now going to begin the live Q&A, and I'll hand over to our Q&A chair, Alan Taylor. Alan, over to you.
Yes, hello everyone. I'm sure you enjoyed Darryl's presentation, and he's one of the few people in the uranium business that's had direct experience with membranes, so he's a good person for you to ask questions. We've got a question now. I'll just read it out. Hi Darryl, this is from Fatima Niku. Hi Darryl, very interesting presentation. Is there any publication on the specifications of designed membrane?
Thanks, Alan. Look, my understanding is that there are no specific publications, indeed general publications in this area. And as it was either in this or in a later presentation I'm giving, that we use membranes well outside the manufacturer's declared or recognised operating conditions. So even manufacturers are unable to help in terms of how their membranes are applied.
Okay, thanks for that. If you have any more questions, please put it in. We've got 10 minutes, a short time, and then of course you'll have an opportunity to participate in the panel this afternoon, at least this afternoon our time. I'll just throw in a question, Darryl. If we have a greenfield, we understand your applications were brownfield. If we have a greenfield operation and we're starting a project, could you just say something about the level of test work you would need in order to include a membrane installation in your project going forward?
Yeah, for sure. So yeah, these applications were brownfield. I'm currently doing a greenfield a project at the moment. Well, we're at PFS, so the test work's begun. I don't see it as particularly different to any hydromet process, in that lock cycle testing in close association with a multi-element computer model to drive the test work to a repeatable outcome and predictable outcome. It works as well with membranes as it does with anything else. Indeed, even though we had brownfield application in this case, and we were able to take existing process streams, what we weren't able to do was see the impact of what we were doing within that process. So we weren't able to show the recycle effect, the return effect of the membrane processing. So and what we did, we did flat sheet testing, and as long as there's some knowledge around of the industrial application of membranes, that flat sheet testing is good in terms of determining just what discrimination you're going to get. In our experience, performance was far better than prediction, which is always a good way to go. And this is an emerging field too, so we were necessarily conservative in the design choices we made. And further than that, we took the time during the design phase to really critically look at the circuit, identify the potential risks, and we had numerous mitigation strategies, pre-developed mitigation strategies ready to go should any of those risks have come home. Thankfully, they didn't. As I'll speak later on, I think today, we had a very, very successful application on two sites. That does, I think, get down to the design effort that goes in. It's a new field. The design and the caution has to match the newness of the field.
Okay. Any other questions that anyone? Just go ahead and type them into the chat box. Just responding that, Darryl, if if you did have a problem and you needed more membrane area once you get an operation, is that a difficult thing to expand?
No.
It's a
No, indeed, Alan. We had spare slots in the design. For, as I said, we sort of done our risk assessment as carefully as we could, and had done or had mitigation strategies in place. Some already installed and not used. Others ready to go should they be needed. Expansion of a membrane plant, as long as the design acknowledges that expansion may be necessary, no, it's not hard. These things are awfully modular, and they're, for the work they do, they're relatively cheap. So they're certainly not a cost driver in terms of capital, and yet they replace, well, in some cases, I was going to say they replace significant portions of plant, but in many applications, they create a discrimination tool, a method of separation that we just don't otherwise have. We can now separate, as was said in that keynote, we can now separate in terms of the ionic charge and valence. That's an extraordinarily powerful tool, and one that we haven't had previously.
Okay, there's another question from David Whittle. I'm interested to know about any models that might be available for estimating cost for service of membranes, where service is some separation function. Oh, that's a question, yeah. I'll just repeat that. I'm interested to know about any models that might be available for estimating cost for service of membranes, where service is some separation function.
Again, the only models I'm aware of are those that we have in-house. To my knowledge, there are only, until I heard about the Kazakhstan plant that's also presented at this conference, my understanding was that we were the only 2 commercial applications. There are, again, to my knowledge, now 3 commercial applications. It's not held within the broader engineering consultancies, the engineering houses. It's certainly not held by the membrane manufacturers. It's very much, my understanding would be that the knowledge is very, very much limited to those that have actively applied membranes themselves.
Okay, good. Just a question on that one. Would you, as far as delivery of membranes, and that are they, you would keep a stock of membranes on site as a replacement, or are they long delivery, or what's your comment on that?
They're not particularly long delivery, but like anything, you can get caught. Like any supply item, you can get caught out. Typical supply cycle into Africa, for instance, which is where our experience is, would be 12 weeks. I'd expect a similar supply cycle into Australia. If you're in the US, you'll get them faster because most are manufactured in the US, some in Europe. And it depends on the application too. We incorporated membranes into an acid circuit and an alkali circuit. In the acid circuit, membrane life was quite low. In fact, our design, and I'd cover, I'm sort of preempting my later paper, but in design, we only assumed 11 days membrane life. We achieved far better than, well, more than double that, which still isn't very much. But yeah, so we had supply chain and membranes on site to accommodate that. In the case, in the alkali circuit, we budgeted on a membrane life greater than 12 months. The experience would now suggest those membranes is properly looked after, and that includes proper cleaning and reasonable stewardship of the membrane. We'll get a significant multiple of the year we budgeted on them. I would expect in excess of 5 and maybe more.
Okay, thanks very much, Darryl, that fills the question time, and I look forward to all the delegates who can join us on the panel and continue the conversation later on. Thanks a lot, Darryl. Appreciate that.
Cheers. Thank you.